Beneath the tranquil waters between Italy and Sicily lies a volcano few have ever heard of, yet it is larger than many of Europe's most famous peaks combined. It does not erupt into the sky or send ash drifting across continents. Instead, it sits in silence, slowly weakening from within. Scientists are not watching it for signs of an explosion, but for something far more sudden and devastating. What if the real danger isn't what rises from the sea, but what collapses beneath it? And if it does, how much time would anyone in Sicily have to react before a massive tsunami reaches the coast? The Marsili Volcano is the largest submarine volcano in Europe, stretching roughly 70 kilometers in length and 30 kilometers in width along the floor of the Tyrrhenian Sea. Located about 150 kilometers west of Naples, between mainland Italy and Sicily. Rising nearly 3,000 meters from the seabed, its summit still remains about 500 meters below the ocean's surface, keeping it hidden from view and largely absent from public awareness. Geologically, Marsili sits within a complex and highly active tectonic setting. The Tyrrhenian Sea itself is part of a back arc basin formed by the subduction of the African plate beneath the Eurasian plate. As the African plate sinks, it generates magma that rises through the crust, feeding volcanic systems across southern Italy. While volcanoes like Vesuvius and Etna dominate attention on land, Marsili represents a vast submerged extension of this same tectonic engine. Unlike a symmetrical cone-shaped volcano, Marsili is elongated and irregular, built from successive layers of volcanic material over hundreds of thousands of years. Its flanks are steep, its structure uneven, and its composition complex. Hydrothermal activity continues beneath the surface, circulating hot fluids that weaken its rocks over time. Although Marsili is an active volcanic system, it is not defined by explosive eruptions, but by slow, largely unseen geological processes. That is precisely what makes it dangerous. Massive, active, and hidden beneath the sea, Marsili remains largely invisible. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. The greatest concern surrounding Marsili is not its magma, but its structure. Unlike solid, well-consolidated formations, much of the volcano is made of fragmented volcanic deposits that were never fully compacted into stable rock. This makes the entire structure inherently weak and prone to failure. This instability is intensified by hydrothermal systems within the volcano. Hot fluids circulate through its interior, chemically altering the rocks and reducing their strength and cohesion. This process, known as hydrothermal alteration, weakens the volcano from within, creating hidden zones of structural weakness beneath what may appear stable on the surface. Studies conducted by Italian researchers have identified sections of Marsili's flanks that are particularly fragile. These areas show signs of structural imbalance, where steep slopes are supported by weakened material. In geological terms, this is a dangerous combination. Over-steepened slopes are prone to collapse, especially when triggered by external forces such as seismic activity or internal shifts within the volcano itself. This is not a unique phenomenon. Similar failures have been observed in volcanic islands like those in Hawaii and the Canary Islands, where massive flank collapses have occurred in the past. In those cases, entire sections of volcanoes slid into the ocean, generating powerful tsunamis. Marsili may follow a similar path, but because it lies underwater, its instability is far less visible. The implication is clear. The greatest threat is not an eruption, but a sudden collapse into the sea. The idea of a submarine landslide triggering a tsunami is not theoretical. It has happened before, and at scales that reshaped entire coastlines. One of the most well-documented examples is the Storegga slide off the coast of Norway around 8,000 years ago. A massive section of the continental shelf collapsed, sending enormous volumes of sediment into the North Atlantic. The resulting tsunami struck coastlines across Norway, Scotland, and beyond, leaving geological evidence that is still studied today. In the Pacific, the Hawaiian Islands provide another powerful example. geological records reveal that parts of volcanic islands have collapsed catastrophically in the past, generating mega tsunamis that traveled across entire ocean basins. These events were not caused by explosive eruptions, but by the sudden structural failure of volcanic flanks. Even in the Atlantic, concerns have been raised about potential collapses in the Canary Islands, particularly on La Palma, where steep volcanic slopes and unstable rock layers present similar risks. These parallels matter because they demonstrate a key point. Volcanoes do not need to erupt to be dangerous. In many cases, their most destructive behavior comes from collapse. While Marsili has no recorded catastrophic landslide, its structure closely resembles systems that have failed elsewhere, making it capable of generating tsunamis through sudden collapse. In recent years, Marsili has gained scientific attention, not due to eruptions or earthquake swarms, but because of what lies beneath the surface. Advances in seafloor mapping and geophysical analysis have allowed researchers to study the volcano in greater detail. Italian scientists, particularly from the National Institute of Geophysics and Volcanology, have identified weak zones along Marsili's flanks. High-resolution mapping shows steep slopes made of fractured and poorly consolidated rock, indicating that parts of the volcano may be structurally unstable. This has shifted concern from eruption risk to the possibility of collapse. Unlike Etna or Vesuvius, Marsili has shown no recent eruptions or significant seismic unrest directly linked to it. Its activity is largely hydrothermal and deep, making it difficult to monitor. At the same time, attention on submarine hazards in the Mediterranean is increasing. While less known for tsunamis, the region has experienced destructive waves triggered by underwater landslides and earthquakes. Despite this, Marsili remains under-monitored due to the challenges of deep-sea observation. Scientists rely on periodic surveys rather than continuous data. The concern is not immediate activity, but the presence of a large, unstable structure that could fail without warning. If a significant portion of Marsili's flank were to fail, the sequence of events would unfold with alarming speed. It would begin with a structural collapse, potentially triggered by an earthquake, internal weakening, or gradual instability, reaching a tipping point. A large mass of volcanic material, possibly millions of cubic meters of rock and sediment, would detach and slide down the slope into deeper water. This movement would accelerate quickly, driven by gravity and low resistance from water-saturated sediments. As the mass descends, it displaces vast amounts of seawater. This sudden displacement is what generates a tsunami. Unlike wind-driven waves, tsunamis are caused by abrupt seafloor movement. The energy from the collapse transfers into the water, producing waves that spread outward in all directions. In deep water, they travel quickly with low height, but as they approach shallow coastal areas, they slow down and grow taller, concentrating their energy. For Marsili, proximity to land makes this scenario especially dangerous. Located near the southern coasts of Italy and Sicily, tsunami waves could reach shorelines within minutes, leaving little time for warning or evacuation. Regions such as Calabria, Campania, and parts of Sicily would be among the first affected. Waves several meters high could flood ports, marinas, and low-lying urban areas, along with extensive tourism infrastructure along the Mediterranean coast. Unlike the Pacific, the Mediterranean is less prepared for such events. With dense coastal populations, millions are at risk. This would not be a gradual disaster. It would begin beneath the sea and strike the coast within minutes. Monitoring a submarine volcano like Marsili presents significant challenges. Unlike land-based systems, deep-sea environments require specialized equipment that is costly and difficult to maintain. As a result, most data come from intermittent surveys rather than continuous monitoring. While seismic networks can detect regional earthquakes and sonar mapping can reveal structural changes, real-time insight into Marsili's internal condition remains limited. This lack of continuous monitoring complicates early warning efforts. A collapse might be detected through seismic signals or ocean sensors, but the short travel time of a tsunami would leave only a brief window for alerts. Efforts are underway to improve tsunami warning systems in the Mediterranean through expanded sensor networks and communication systems. But these are still developing and depend on rapid response. Preparedness is also limited. Public awareness of tsunami risk in the Mediterranean is relatively low. Emergency planning, evacuation routes, and education all play a role in reducing risk, but only if the threat is recognized. Marsili highlights a broader challenge in disaster management. Some of the most dangerous hazards remain hidden beneath the surface, where monitoring and awareness are limited. Marsili Volcano represents a low-probability, high-impact risk. There is no evidence that a collapse is imminent, and it may not occur for hundreds or thousands of years. However, the conditions for such a failure exist. This uncertainty makes the threat easy to overlook, even though history shows that submarine landslides and resulting tsunamis can occur suddenly with little warning. Continued research and monitoring are essential. Advances in seafloor technology, sensor networks, and modeling may improve detection and risk assessment, while greater awareness and preparedness could reduce potential impact. Marsili is a reminder that powerful geological threats can remain hidden. It may not erupt or draw attention, but its greatest danger could come from a sudden collapse beneath the sea and the wave that follows instantly.